Hello, and welcome to the lecture for Chapter 15 from Conceptual Physical Science, 6th edition. In this chapter, we're going to talk about chemistry some more, because we just started talking about chemistry in Chapter 14. So this is really just our second chapter in the formal field of chemistry, although arguably the two chapters before set the stage for all of this. So hopefully you've been along for the whole ride, and this journey through the physical sciences is continuing on its way for you as well as for me. Anyway, here we're going to talk about how atoms bond. I hinted at this quite a bit in the last lecture. I'd highly recommend you check it out because it's a big open question. We talked about molecules. We said that there's compounds made of molecules. Chemistry is all about studying their interactions. But why are there molecules? Well, let's answer that question. Simply put, let's answer that question. Okay? So we need to find out what holds molecules together, what attracts the atoms within a molecule. And to do that, we're going to first establish a convention. How do we consider molecules in terms of their outer electrons? Okay, and that's going to be the electron dot structure. And by the way, to get there, we have to understand a term called valence electrons, and we'll see this in just a minute. Valence electrons, and that's going to take us back to understanding the conceptual model of electron shells. Please review electron shells when we talked about the atom. Okay, now we'll also talk about the formation of ions, this idea of there being missing electrons, which is just the number of electrons does not match the number of protons. That's any time you have an ion. And again, we defined that back when we defined atoms. Then we'll talk about ionic bonds, which of course includes or represents ions. Ions are part of those bonds. Then we'll talk a little bit about metallic bonds. Not too much to say there, just that it's going to take us to bonds in metals, what's happening there. And recall in metals, I think the most important thing that we should really focus on is free electrons, because that was the whole idea that make metals both a good conductor of heat as well as electricity. But then we're going to get into the real meat of this lecture, which is talking about covalent bonds. That's sharing of electrons in those valence or sharing of valence electrons, which is to say electrons in that outermost shell. We'll also talk about polar covalent bonds, how the sharing of electrons isn't always equal, and therefore it creates a polar molecule because there's a polar bond. What's interesting here is we're using the word polar, which means poles, like a north and a south, but we've actually used another term that describes this equally well back in our chapters on physics. And it's kind of interesting because it's really a representation of how physicists might use one word and chemists might use another. But what we're talking about here is a dipole, all right? So really, a polar molecule is just a dipole. That's all it is, okay? It is a dipole. It is some electrical object that has two poles, a positive pole and a negative pole, because we don't call them, north and south for electricity. We call it north and south for magnets. But here we're talking about a dipole. That's it. Okay. Hopefully that's familiar. Go ahead and go back and review dipoles. It's that's when we were first introduced electricity. So important to this chapter, and I'm going to be referring to that quite a bit. Then we'll talk about that more about that idea, molecular polarity. That's definitely going to take us back to dipoles. And then we'll finally talk about how those dipoles create all sorts of attractions based on what? Well, none other than the Coulomb force. Everything we talk about, all these attractions, and there's a whole list of them. We're going to have dipole-dipole attractions, induced dipole-dipole attractions, induced dipole attractions. It seems like a lot to remember, but really it's the Coulomb force for every one of them. Every one of those. There's always one force behind the scenes that explains it all, which is so important to the physical sciences, being able to simplify things just to a few governing rules, all right, the laws. All right, but let's get into the content here. All right, spent plenty of time on the table of contents. Okay, so first of all, I said we needed to learn a way of representing something, a new convention, right? A new set of rules, and that's electron dot structures. Essentially, I want you to learn how to draw these and how to read the drawings, and you'll see what I mean. So atoms bond together through their electrons. It is the electrons that hold atoms together. Simply put, the nucleus plays no role in holding atoms together, truly. To learn about bonding, therefore, we need to know something about how the electrons within an atom are organized, okay? Again, we don't care about the nucleus, all right? So, electrons behave as though they are contained within a series of 7 concentric shells. What does that mean, right? It means that down here, this tiny little dot, where most of the mass is the nucleus. outside of the electrons. But the electrons obey the quantum hypothesis. There's all these sort of rules of them behaving like waves. They are particles, but they're also waves. And that results in a understanding of the atom as shells of electron potential energies, okay? As we get further away from the center, we are gaining potential energy. So electrons further and further away have gained more and more potential energy. They can fall in further, okay? But if there's other electrons in the way, if all these inner shells are full of electrons, well, they're not going to fall in. They're just going to stay out there in these high potential energy, very distant shells. And that means that those shells may be filled up permanently. Unlike an excitation of an electron, where the shells are open, the upper shells as well as the lower shells. In that case, the electron jumps up to a high shell and then jumps back down. Nope. Here, since all the electrons are there, many electrons, a matching number of electrons to protons, there's nowhere for those outer electrons to go. They stay up in those outer shells, okay? And that has so many effects because that means those faraway electrons, since they're so far away from the nucleus, they can do things like feel forces from the electrons of other nearby atoms. And of course, that leads to molecular attraction, okay? Now you might think, well, but aren't they sharing the force? Wouldn't they just push each other off? And that's absolutely true. If I have an electron out here and there's another electron nearby in an outer shell of another atom, then the natural thing for an electron to do to another electron is push it away. There is an electrostatic repulsive force. But what about that attraction towards the nucleus? What about the fact that there is a nucleus after all that's pulling the electron in with positive charge? Well, that means that might be another nucleus nearby that's also pulling the electron in with positive charge. And it's that pull of neighboring nuclei. Okay, again, we don't care so much what the nucleus is doing other than that it plays a role of pulling on other electrons that allow molecules to form, allow for attraction. Okay, now I won't talk about that too much because we're going to get into the idea of sharing electrons and simply, electrons getting bonded together. But ultimately, it is all about the attraction between outer electrons and neighboring atomic nuclei. Okay, all right. So do note, as I said a couple times, this is totally a conceptual model. Atoms really do not look like this. The electrons, they're a probabilistic phenomenon. There's something called the Heisenberg uncertainty principle. So there actually is no defined shape, but there's a probabilistic shape, and it doesn't actually look like this, except for a couple of atoms, it is symmetric in spheres. Most of them actually have other shapes, but again, they're probabilistic shapes. But not important. We have a good conceptual model to understand the idea of outer electrons in shells far away from the nucleus, okay? It helps us understand how electrons behave within atoms, okay, and ultimately between atoms as electrons get pulled from neighboring nuclei. Okay, so the shells, this conceptual model, are more easily drawn in 2 dimensions. We're never going to draw them in 3 dimensions again, okay? So let's consider helium, okay? Not the smallest atom that's out there, the second smallest. It's got an atomic nucleus with 2 protons as well as 2 neutrons, and it's got 2 electrons. Okay, it's got 2 electrons in a shell that fits how many? Yep, 2. That means that its outermost shell is full. You can't fit any more electrons there, okay? Let's consider neon. Well, neon is a case where there's also going to be the first shell filled with 2 electrons. But then there's the second shell, the next layer. And again, this would have been an excitation level for helium, or at least a similar amount of energy. But for neon, it's actually full. It's not a point of excitation where electrons jump to. Instead, it's a point of population. Electrons are there all the time. And how many are there? Well, 2 plus 2 plus 2 plus 2, 8. Okay? Is that how many fit in the second shell? Absolutely. 8 electrons fit in the second shell. That means that neon has 2 full shells. And so on for argon. Argon has 3 full shells. So these examples, these elements, helium, neon, and argon, have completely full shells. Notice that they're all over here in this group of the periodic table. That group has a name called the noble gases because they're full, they're noble, they don't like to mix with others, they're snooty in that sense of noble, and it means that they don't bond, practically, physically, science speaking. They don't bond because they have full electrons in their shells. In other words, they have full shells, I should say, okay? That means full shells don't lead to bonding. We're really not going to talk about helium, neon, and argon, or any of the gases in this column, which is to say in this group, because this whole group, this column in the periodic table, don't form molecular bonds. Okay, well, but they're the exception because there's a whole rest of the periodic table, and everything there isn't going to have full outer shells because of the way it works. Because the periodic table is just counting protons, which means it's just counting electrons, which means it's counting how many electrons fit per shell. It means every other spot is going to have available spots in the shells. Okay? All right. So each atom has its own configuration of electrons. Elements in the same group have similar configurations. Remember, group is going to be column, which is why they have similar properties. So all these ones, neon, helium, and argon, have similar properties. They don't bond. Okay, so the term is valence electron. Those are the electrons in the outermost shell that's filled because all these subsequent lower shells are, well, partially filled at least, and it's that valence, those valence electrons are there in that whatever shell it may be, the second, the third, the fourth, the fifth, the sixth, whatever it may be, right, all up to the seventh, because again, all the lower ones are completely full. Okay, but those lower ones being completely full, they're electrostatically balanced. They don't play a role in bonding. Okay, so we only care about the valence ones. They're the ones, the electrons that is, that lead to chemical bonding. Okay, so that means that we can draw the number of electrons in those outer shells by using little dots that we actually put around the letter. And it's really the same idea as this. Like imagine here I wrote the letter Ne, and then I started drawing little dots around that Ne. That's what the so-called dot structure of drawing molecules is about. And it's useful because it tells us when we should expect bonds. Okay, and you'll see why in a few moments. Okay, so that's the dot structure. Let's consider a particular element, chlorine. Okay, all right, we already saw chlorine making molecules in the naming convention in the previous chapter and its lecture, and we saw something like chloride, right? Okay, but here's chlorine by itself. We haven't formed a molecule with it yet. We're just considering it on its own. Check it out. It obviously has electrons in the second shell. We actually don't know if it's the second or third shell because it turns out that both of those hold the maximum of 8. We saw that back in the figure a couple slides ago, right? Both the second and third shell hold up to 8 electrons. So we don't know if it's the second or third. It turns out it is the second for chlorine. And we see that chlorine has how many of those 8 full? Well, 7, okay? And that means there's one set that's unpaired. The pairing is so important, okay? Because the pairing means that there's going to be an equal attraction force to the nucleus between this electron and a neighboring chlorine molecule, all right? Atom, excuse me. On the other hand, there's carbon. Well, carbon filled up that first shell, right? But carbon then, there's going to be 2. And notice we're not drawing the first shell because we're only drawing the shell that isn't completely full. Every time we do this dot structure, electron dot structure, we only ever draw the shell we care about, which is to say the last shell that's partially full. All right. So both these, chlorine and carbon, have an inner shell, the innermost shell, the one that only holds 2 electrons, and it's full, but doesn't show up in the diagram, does it? Because we don't care. Okay. So again, with carbon, where there's the second shell, holds 8. How many are there? Well, there's only 4. And they get distributed evenly because they're going to be repelled from each other. So we think of them as evenly distributed. All right. Remember, like charges repel. Okay. Opposite charges attract, of course. Okay. So how many then? That means that there's only 4 out of 8, which means that there's a lot of unpaired ones. There's effectively 4 unpaired electrons. Get it? Okay. We're going to see that again. Okay. But for now, just consider how we're drawing these. So for heavier atoms, some valence electrons are more available than others. So krypton, for example, has 18 valence electrons, but only 8 of those are typically shown with an electron dot structure. These are the 8 that extend furthest away from the molecule, okay? And they're all full, by the way, so this krypton isn't going to easily bond because it doesn't have any unpaired electrons. So we can think of it as being, it's kind of a trivial case because, hey, look, I mean, what does it tell us? Well, it tells us the same thing as if we drew 18 dots. But practically speaking, we wouldn't want to draw 18 dots. They don't really fit. So we just draw those outermost 8, okay? Now, that said, you shouldn't worry about it too much because we won't be dealing with those heavier atoms and the molecules they form. So really just focus on ones that really just have a second or third shell, a shell that would hold 8. Okay, all right. And just to review and to bring this back home to the periodic table, right? The ones we're going to be talking about, the atoms you care about, are going to be these ones here, okay? The non-metals. That's because metals have their own type of molecular bonds. And again, this is kind of a passing note. It's not our main focus. There's just not the same story to be told, okay? All right, this is just not a very strong force. But we really care about these atoms. Now remember, these elements, these ones here, the noble gases aren't going to come up much because they don't form compounds, they don't form molecules very easily. But all these other ones, right, including the ones in the first two groups, and then the 13th, 14th, 16th, 17th, and 18th groups, these are super important to understanding how molecules form, okay? And we see lots of good examples of those dot structures. Notice how many unpaired, outer or unpaired valence electrons they are in each case, okay? Go through and make sure you can check it for yourself. Like right here, right? For sulfur, how many? 2 unpaired valence electrons. What about for titanium, right? Well, in this case, there's 3 unpaired valence electrons, and then a full-on spot where there's just none, okay? All right, let's do one more. What about carbon? We did that one before, do you remember? 4 unpaired valence electrons. Excellent, okay. So sodium, Na, atomic number 11, all right, has only 1 valence electron. Upon losing this electron, what other atom in the periodic table does the sodium thus resemble? Now, why do we know it only has 1? Well, because it's got 2 in the first, and then 8, that's 10. So that means its first and second shells are completely full. 2, 8, right, in terms of the shells. And then the next one holds 8, but there's only 1 there. That's why it only has 1 valence electron. So what happens then when it loses that valence electron? What does it resemble? All right, neon with an atomic number of 10, magnesium with an atomic number of 12, lithium with an atomic number of 3, or sodium can only resemble sodium. Which is it? Molecular speaking, what does it behave like? Neon, right? So if we have ionized sodium, and we'll talk about that term again in just a moment, which means we've changed the number of electrons from a balanced state with the nucleus. But in this case, we've ionized sodium, we've had it lose an electron. It still has the same number of protons. It still has the same atomic mass. Nuclearly speaking, it's definitely still sodium. But molecularly speaking, it would behave like neon, all right? So the sodium has enough electrons to fill the first and second shells, just like neon. Okay, and we'd write that, right, because it's lost an electron, we'd write it ionically as a plus to show that it is a positive ion because it now has a net positive charge because still has 10 of those protons, right? So 10 protons, right, or 11, excuse me, because it's neon, but now it has 10 electrons because it lost one. Okay. So there's two things there, right? There's the idea that it's an ion and the idea that molecularly speaking it's behaving like neon, which is to say it wouldn't form a molecule anymore because it's effectively a noble gas. Okay, all right, right. A lot of ideas, but hopefully it's painting a good picture here how these molecular bonds work. So as I promised, we're going to talk about ions. Good segue. Okay, so an atom that has lost or gained one or more electron, just like the sodium we were talking about. That sodium lost one. Okay, so for example, we have sodium here with 11 and 11. 0 net charge, it's balanced, okay? Most atoms out there are going to be naturally balanced. It takes energy to turn them into an ion, okay? But in high energy states, there's just plenty of physical examples, ions are created, right? Remember, a plasma is an ionized gas, right? The sun is all plasma because it's so high energy. All the gases are ionized, okay? So here, excuse me. So here we still have, sodium, but now there's still 11 protons, but only 10 electrons. So now there is that plus 1, okay? Plus 1 what? Well, plus 1 of the fundamental charge. And it's plus 1, the fundamental charge, I'll just remind you because it's not just, just some arbitrary thing, it's actual physical quantity of units, is 10 to the negative 19 coulombs. That's how much charge there is per electron, okay? But that's how much there would be, plus 1 of those, okay? Because now there's a vacant valence shell for this positive ion of sodium. Good. Okay. By the way, positive ions of sodium are super important for human biology. They allow us to create ion channels between our neurons, which allows us to think. Good news, right? Okay, another example. We have fluorine. All right, 9 protons, 9 electrons when it's balanced. Okay, that's its atomic fluorine. But then we can have a negative ion of fluorine where it has actually gained an electron. It gained an electron because now its outer shell, which only had 1 empty space, unlike chlorine, which only had 1 full space. This is the opposite. It has 7 out of the 8 full spaces and only 1 empty space. It got filled. Now, it's no coincidence that our two examples here of creating a positive ion of sodium and a negative ion of fluorine involve having a basically full valence or completely empty, either completely full or either completely empty valence shell, because that can easily happen. Okay, especially if you're only 1 electron away from completely filling a shell, or you're only 1 electron away from completely vacating a shell, then that takes far less energy than say removing 4 electrons to vacate a shell. Okay, and there's an energetically favorable process to have a completely vacant or completely filled shell. Okay, so definitely that's why these are common ions. It's less energy to create them. All right, so how do ions get formed? Well, let's consider a type where we just got a floating around hydrogen ion, right? It's just out there in the environment, and that's because there was some process that ionizes hydrogen. Because by the way, ionized hydrogen just means a single proton, because that's all there is in the nucleus, that's lost its electron. Its electron, went flying off into nowhere, and it was left with a net +1 charge, right? It's like one of the most fundamental, very easily created particles out there. It's a single proton. Lots of like a fire would create single protons, right? Like any high energy process. Well, then this naturally created hydrogen ion is flying off through space and it's going to interact with something, right? So it's going to find something and bump into it. So here we go. It's moving through space, and there it goes. It comes into contact with a water molecule, and in doing so, it creates another ion. In this case, creating a hydronium ion. So this is how ions get created and perpetuated. One ion leads to another. Okay. Now, of course, this ion may bond with a negative ion and then become neutral again. There's plenty of examples of that happening, but here we show an example of an ion creating another one. Okay. So this also leads to ionic bonds. So this is the electrical force of attraction between oppositely charged ions. And this is the idea of two ions becoming neutral. So like one positive ion meeting a negative ion, the two of them coming together and becoming neutral. Let me show you what I mean. Okay. So let's consider a positive ion of sodium, again, very easily created due to the propensity of that valence shell getting completely vacated or completely filled. Same story for fluorine. Okay, well, here we have these two naturally created ions. They're going to want to come together. There's going to be a Coulomb force pulling them together. We have opposite charges, of course, so they get brought together, and voila, we end up with sodium fluoride. Okay, pretty cool. All right, so what is the chemical formula for a compound made of aluminum ions, which have a 3+? Notice, at this point, we've only seen a single plus. That means that we're missing 3 electrons. Okay, this is aluminum missing 3 electrons, not just one. And O2-, that's an oxygen ion that has 2 extra electrons. Maybe and that might throw you off that extra means minus and missing means plus. And that's because we care about the electrons. And of course, electrons have negative charge. I should definitely call attention to that because I remember that confusing myself when I was a student. All right. So then, of course, losing electrons means gaining positive charge. Gaining electrons means gaining negative charge. Good. Okay. So what's formed between that aluminum and oxygen? Well, we get A2O3. Okay. And really nice to see. This is a really nice diagram here, nice picture. You can actually zoom in here and look at the bond, and you can see what's going on in terms of our aluminum, right, bonding with and sharing its valence electrons with these oxygens, so that the ions all become neutral. See, right? They want to all share those spots. In each case, we have a valence electron sharing with another valence electron. Now, this really is going to be the same idea that we're going to see when we see covalent bonds, this idea of electrons pairing up, right? So if there is already a pair, they're not going to pair up. But if there is a missing pair, then they will pair up, see, each time. The only thing that doesn't make this a covalent bond, the topic that we're just about to start in a slide or two, is that it involves ions. That's what makes this an ionic bond. And it's actually a really strong type of bond because there was already these electrons that were already unbalanced, or these atoms that were already unbalanced. So ionic bonds are particularly strong because they're just everything is leading to a desire for them to stick together to become neutral. Okay? All right, good. But that definitely sets the stage to move on to actually just talk about this idea of sharing electrons more generally and not specifically to ions. Okay? But first, what is more about ionic bonds? What is the chemical formula for a compound made of a magnesium ion with 2 missing electrons and an oxygen ion, again, with 2 extra electrons? Okay? Well, in this case, it'd be MgO. They would just pair up as a single, right? So just be a single magnesium and a single oxygen. And I should call attention to that. The reason is because 2 and 2, well, that just sums up easily to 0, right? So I'm just taking 2 plus -2 equals 0. We weren't able to do that with a single atom of each in our last molecule. Why? Well, because we had 3, and 3, plus -2 does not equal 0. So how are we going to do that? Well, the only way to do that and have an integer number of atoms, because you can't have half an atom, but not the only way, but the minimum way to do this, it's like a puzzle. The minimum way to do it would be to have 2 of the +3, which is of course, the aluminum, plus 3 of the -2 of the oxygen. And you're just kind of thinking of the common denominator here. And then that does, in fact, give you 0. And that's what you need because it has to become neutral because there's this attractive force that wants to make it neutral. It's the least potential energy. So it's the idea of losing potential energy to get, or transferring the potential energy of this electric field into the bonded potential energy of the molecule. Okay, and that's an energetically favorable process. Right, it wants to happen. Right, but here we just need 1 and 1. Okay, so it's all about counting how many missing or gained electrons there are in your initial ions that are going to form your ionic bond. All right, so enough about that. First we're going to talk about metallic bonds, and we'll finally get to covalent bonds, the main meat of the lecture. Okay, but first, real quick about metallic bonds. Metallic bonds have outer electrons, right, or in those metal atoms that are held on very weakly. Okay, so the inherently metal has very weak outer atoms. So that means that the weak attraction allows the electrons to move about quite freely. So they're like free agents. An electron really isn't held to its nucleus. It can move among all the nuclei of that metal. So this mobility of electrons accounts for many metallic properties, right? Conductivity being the big one. And that's conductivity of electricity and heat. Good, all right? So an alloy is a mixture of metallic elements. Good, all right? Like here, we have an alloy that forms this Liberty dollar, all right? Okay, good. And again, what holds the alloy together? Metallic bonds. It allows metals to stick to other metals. That's why you can often mix metals together and they continue to, they don't just they don't stay apart, right? You can mix tin with aluminum or something, right? Melt them together and mix them together and they'll form that alloy. That's because of that ability to freely share electrons, okay? Good. But enough about metal, not too much to say there. Let's get on to this idea of covalent bonds. And again, covalent bonds is going to be all about sharing unpaired electrons, just like I talked about a moment ago for ionic bonds. The difference, though, is it doesn't involve, like I said, it does not involve ions. It's taking two neutral atoms that have unpaired electrons in their valence shell and bonding them up. Okay, so it is the type of electrical attraction in which atoms are held together by their mutual attraction for shared electrons. Right? Both the nuclei want those electrons. They come together with equal force, right, or maybe unequal force, and you got yourself a bond. Right? Good. Okay. So, for example, fluorine and fluorine can form a fluorine molecule, difluoride. Okay. Two fluorine molecules together. Why? Because they want to form a covalent bond, a sharing of electrons, because they each have one and only one unpaired electron in their valence shells. Okay, good. So there are two electrons within a single covalent bond. As you can see, the bond is this whole thing here. It involves two electrons, one from each atom. Very good. The covalent bond is represented using a straight line. When, right? This doesn't look like a straight line here, right? These are like kind of curved arrows. Well, in the dot structure, all right? So you can actually use the dot structure to draw covalent bonds, right? Now notice when we do the dot structure, we often leave off the dots, but you don't have to. Sometimes you'll see the paired electrons of the original atoms left in there, and then the covalent bond is shown on top of that. Every line represents two electrons. Every line represents two electrons, right? And represents a covalent bond. Got it? Okay. So the number of covalent bonds an atom can form equals its number of unpaired valence electrons. That's why fluorine can form one covalent bond because it has one unpaired electron. Good. Okay, what about oxygen? Well, we talked about before by reading the dot diagram of oxygen, that oxygen has not one, but two unpaired electrons. That means that it can bond up with two things, okay? So it can bond up with two hydrogen atoms because hydrogen each has one unpaired electron, okay? And of course, hydrogen has that special role being the only atom out there that has an unfilled first shell, right? Because helium, you only need two to fill that first shell. Helium already has two, and it's a noble gas with a full valence shell, okay? But hydrogen isn't. Hydrogen can absolutely form covalent bonds, and it regularly does, right? So then we can then take those two hydrogens and the one oxygen, pair up, right? Shown here in blue, we have two covalent bonds because we paired up both of the unpaired electrons, and we got ourselves a water molecule. Excellent. Covalent bonds formed a water molecule, H2O, okay? There's other examples. So for example, we have here nitrogen, all right? Well, nitrogen, when it forms up with three hydrogen, each with its own unpaired electron, because, and the reason it does that is because it already has 3 unpaired electrons. It has a very unfull outer shell, right? And so then it has a special name, that's ammonia, okay? Right? NH3, very good, right? And there's that one non-bonding lone pair that got left behind. But there's a very special atom out there that has 4 pairs, 4 out of 4, ready to go, and that of course is carbon, right? All of its electrons are unpaired. It doesn't have any that are pre-paired. That's fun, pre-paired, you get it? So that means that then it can form with, or form a molecule with 4 hydrogen, for example. Now we keep using hydrogen as an example. That doesn't mean that all molecules have hydrogen in them. It's just a simple example to show, And these form very common gases, important both here on Earth and in outer space. Like ammonia is a wonderful example. There's lots of ammonia on other planets. And here we have methane, another very important gas in terms of astronomy, right? And biology and chemistry, okay? So methane from a single carbon and 4 hydrogens, and it forms because you want all of those unpaired electrons to find other unpaired electrons. They indeed have, and we've got ourselves 1, 2, 3, 4 covalent bonds, okay? And I said that carbon is a very special example, and that's because carbon has, those 4 unpaired valence electrons. That means that it can form molecules with lots of different things. Carbon is a super flexible atom in that respect. There's so many molecules you can be part of, which is why we say carbon-based life, because molecular atoms all involve carbon because of that flexibility, that chemical flexibility of carbon. Okay, good. So multiple covalent bonds are also possible. At this point, we've only seen 1 per unpaired electron, but check it out. You can take oxygen. Oxygen, after all, has 2 unpaired electrons. If you take 2 oxygen, then both of their unpaired electrons will fuse with form a bond with the other unpaired electron. That means you basically have 2 stacks of covalent bonds. So these double lines like this represent how many electrons? 4, because they're 2 covalent bonds. Each covalent bond is 2 electrons. So 2 times 2 is 4. Okay, so that's what we're seeing here with this double covalent bond. Okay, so 4 electrons here, the other 4 over here, which makes sense because carbon, right, has the 4 electrons to work with. Okay, good, right? Same idea here. You can actually have a triple covalent bond with diatomic nitrogen. Nice. Diatomic nitrogen is actually very common. It's part of the air that we breathe. Okay, so that's covalent bonds. Tied it back into the idea of the dot structure, showed that it's drawn as a line, talked about how they form, all about unpaired valence electrons. Now, a big consequence, so we're going to move forward, a big consequence of covalent bonds is polarity. Because what happens in many cases of covalent bonds is you end up with a polarized molecule. You end up with a dipole, okay? Okay, so electrons within a covalent bond are shared evenly when the 2 atoms are the same. We saw lots of examples of that. Diatomic nitrogen, diatomic hydrogen shown here, okay? Totally balanced, because they're identical after all. Of course they would balance out, okay? Hopefully that makes sense. But there are also lots of examples where they're shared unevenly, right? They're shared unevenly because they're not the same atom. In fact, anytime they're not the same atom, they will be uneven every time. So for example, hydrogen and fluorine. Okay, so that leads to a term I want to make sure you understand, electronegativity. This is the ability of a bonded atom to pull on shared electrons. The greater the electronegativity means the greater pulling power. So which of these 2 atoms, the hydrogen or the fluorine, do you think has the greater electronegativity? This one, okay? The fluorine, because it's got more electrons. It has the greater electronegativity. Okay, so electronegativity increases on the periodic table, and not just strictly with more electrons, but also as we go in decreasing element, okay? So the highest electronegativity are going to be the non-metals found up here in this part of the periodic table. Notice that the noble gases are excluded because they don't really have any electronegativity, but the highest are going to be these elements right up around here, okay, including fluorine, all right? The lowest electronegativity are going to be these down here with high, that have a high period and a low group, okay? All right, so let's look at some examples. So let's look at sodium fluoride, okay? So sodium fluoride, who has the greater electronegativity? We just look at their place on the periodic table, and indeed it's fluorine. That means that the direction of the dipole is going to be towards the fluorine, all right? And by the way, this is also an ionic bond, okay? But it has a strong directional electric field which means that there is a distribution of charge that's not even, and that charge is distributed towards the fluorine, okay? Which means the negativity points in this direction, the negative, the negative charge, okay? Now for the polar covalent bond, right, so a different type of bond, but again, leading to a dipole, right? Well, that's in this case, between hydrogen and fluorine. We saw that drawn with the little dots representing the electrons, okay? And that's going to be like this, okay? Same direction, towards the fluorine, because fluorine has such high electronegativity. And by the way, when we drew the dots like this is hinting at the idea that the electrons are jumping around and their location isn't exactly known. That's why we drew them as these kind of like cloud shapes. It's a common way to draw electrons. I realized I hadn't said that, so I wanted to make sure that was clear, okay? All right, and then the last example, a nonpolar case, because they're the exact same atom, so diatomic fluoride, definitely it's, a molecular fluorine, whatever you want to call it. Well, in that case, it is not polarized, it's balanced, okay? Which is why there's no arrow here showing the direction of the dipole, okay? All right, so this question doesn't actually have anything to do with dipoles. It's just going to be a quick aside, and then we'll get back to dipoles. Which is heavier? But I think it's a good grounding question. Which is heavier, carbon dioxide or water? All right, what are they made out of? Think about that. Which is heavier? Carbon dioxide is heavier? Water is heavier? Or they both have the same number of atoms, so they weigh the same? If you think about it, they both have 3 atoms, right? Well, carbon dioxide is heavier. Because if you look at the periodic table and you look at the atomic masses, throw back to kind of previous chapters where we talked about the nucleus of atoms, we know that carbon dioxide has a weight of 44 atomic mass units, right? This is how many of this very small chunk of mass that is the mass of a proton, okay? And then water only has 18 atomic mass units, so carbon dioxide is definitely heavier per molecule, okay? Just because they have the same number of atoms doesn't mean they have the same weight. So that's just a good reminder, right, of kind of that absolutely weight, physical properties like that still matter, and that's still the case, okay? Now let's go back to chemistry. So back to polar bonds. So polar bonds where there's molecules that are facing equal and opposite directions, they should cancel out, right? Because we looked at lots of cases, if you go back here, where there was just 2 atoms, okay? But what about when there's 3, like in this case, with the oxygen? Well, in that case, yeah, they do cancel out, right? It's like people pulling on 2 ends of a rope, and they can just pull equal amounts, and they balance each other, okay? Right? No one's pulling harder, same force, and they remain at rest. Or in this case, since we're not talking about motion and forces and accelerations, that we're just talking about balancing the electric force, that just mean there's no force, cancels out. And that's absolutely true of diatomic carbon like this, okay? Or carbon dioxide, I said it backwards. So it's absolutely true of carbon dioxide shown here with this dot diagram or valence diagram. And that's because carbon dioxide just geometrically forms in a straight line like that. But it turns out that the actual 2D or 3D geometry of molecules is a bit more complex than we're going to cover in this class, but we're at least going to talk about a case where they don't form in a straight line, and that is water. Because the geometry of water isn't like the geometry of carbon dioxide, and the 2 hydrogens instead form like little ears. And you've, of course, seen this. We've showed this picture throughout many lectures, right? I've shown this picture many, many times of H2O, of the H2O molecule. It's always drawn like this. And for good reason, because this is how geometrically it forms, okay? It's symmetric around the other axis, so it's more 2D than 3D, but it definitely is not symmetric here, right? The hydrogen is down that way. And that means that in the x direction, if you think of an xy axis, so x this way, right, horizontal, y vertical, in the x direction, there is cancellation of the polarity, okay, the dipole, because this component of the polarity cancels out, cancel, cancel. But the vertical component is actually additive. It doesn't cancel. It creates a vertical component of polarity, which is to say electric field, in this direction, okay? And that means that there is a negative end on the side of the oxygen where there's no hydrogens attached, and there's a positive end on the side of the oxygen where the hydrogens are attached. So that means that water is very much polarized. It's a dipole, okay? Every water molecule is a dipole, which means that it essentially has a voltage. It has an electric field, right? It has it's like having, it's like holding charge, right? That means that any other charge that experiences this created dipole is going to want to move along the direction of the field lines. It's going to experience an electric force, okay? Well, that has incredible consequences. Let's talk about them, okay? So one is that when you look at water, it's full of all these dipoles, all this ability to exert force. What does that mean? Well, water has such a relatively high boiling point because water is such a heavy substance, Is it that heavy? Right? It's lighter than carbon dioxide. Is transparent, so the heat passes right through it. Does that have to do with heat flow? Contains 3 atoms per molecule. Okay, we established it does, right? But we also said that it's not really a physical property, right? Because not all atoms are the same. Or is it because molecules are so sticky? That seems kind of vague. What's the best answer? Well, turns out it's the vague one, okay? Because what do we mean by sticky? Well, we mean, we're using a non-technical term to represent a technical idea. And what we mean is that the slightly negative end of one water molecule holds on to the slightly positive end of another. Oh, that makes sense, right? Because opposites attract. So this force of attraction must be overcome before the liquid water can transform. That's why water has such a high specific heat. That's why it takes so much energy to boil. And it really is incredibly high. Water has one of the highest specific heats in the physical world. Wow, okay. All right. So that can also lead to other types of molecular attraction, like ion dipoles. This is the attraction between an ion, which we talked about before when we talked about ionic bonds, and a dipole, like water. All right? So for example, sodium chloride in water, right? So you get these ions in the water, what's going to happen to them? Well, they're going to get attracted to either the positive end or the negative end of this dipole, right? And we know it has a negative end over here and a positive end over there. So which side is the positive ion of the sodium going to get attracted to? The negative end. On the other hand, the chlorine is going to get attracted to the positive end, which is the end with the hydrogens, which is shown in the diagrams. Because notice the way the molecules, the water molecules, are shown. They're shown with the oxygens facing the positive ion and the hydrogens facing the negative ion, all due to electrostatic attraction between opposite charges. Okay? That's called an ion-dipole bond. That means that the water essentially pulls on the sodium, okay? Which means it dissolves the sodium. Have you ever heard that water is the universal solvent? That's because it's a dipole, okay? All right? There's also dipole-dipole attraction. This is the attraction between two dipoles. This is actually what we were talking about when we said water was sticky. Right? Now we got the technical term. Okay? Stickiness of water. Right? The fact that it can have that strong capillary force. You see how you ever heard of water tension, right? You see it every day, how these big droplets of water. That's because water is so sticky, right? But of course, the high boiling point is also indicative of it being so sticky. And it's all because of its dipole-dipole attraction. Every water molecule is attracted to another water molecule, right? Because the positive end of the water molecule is pulled to the negative end of another one, okay? That's a dipole-dipole attraction. Super important for water, okay? And it also explains why ice is less dense than water, okay? Pretty cool. There's also dipole-induced dipole. See, we keep just listing different types of attractions here. And we keep bringing it back to water, right? Well, this is the attraction between a dipole and an induced dipole. But hold on, what's an induced dipole? Well, an induced dipole is taking a otherwise non-polar, which is a balanced molecule, okay, and making it polar. Because once you put it into the voltage, the electric field of our dipole with a negative and a positive end, what's that going to do? Well, that's going to induce a charge distribution. It's going to pull the positive charge over here, and it's going to repel the negative charge of the electrons within the diatomic oxygen molecule, turning it into, yep, a dipole. What type of dipole? An induced dipole. Okay, and now that it has been induced, well, now it effectively has a positive end. That positive end is going to get attracted to the negative end. So you might be thinking, wait, isn't that cheating? That means the water molecule can create the thing that then will be attracted to it? Absolutely. Because after all, the electrons are free to move within the diatomic molecule, right? There are electrons in those shells and their exact positions, right? They're not in perfect shells. After all, we said that was a conceptual model. Their exact positions can change, right? They are, they're particles, they're waves, and they can move around. And that's what happens. It gets distorted. That diatomic oxygen gets distorted and becomes a dipole. Okay, and then attraction. Opposites attract, all right? So held on every time, that's water that's doing it, right? That's water creating ion dipoles with the sodium and the chloride or chlorine. That's water holding itself together. And that's water in this case, effectively holding on to a oxygen molecule. Universal solvent, right? Water can do so much because it's able to take basically anything and hold on to it. Okay. Now, sometimes if say, for example, this is a really big molecule that was balanced, it would be a very small force, so it would dissolve it very slowly. But water will eventually dissolve just about anything. Okay. So a non-polar material such as oxygen, O2, diatomic oxygen, but it's the way the oxygen naturally forms. So when people say oxygen, they actually mean O2, is soluble in a polar material such as water by way of what? Well, if you're paying attention, you know which one it is. Is it ion dipole? Is it dipole-dipole? Or is it dipole-induced dipole? It's dipole-induced dipole, okay? Because the oxygen becomes an induced dipole, and because initially it was non-polar. Got it? Okay. All right. So this is a relatively weak force because in order of strength, this one was the strongest here. The second strongest was the dipole-dipole, and the dipole-induced dipole is even weaker. So that means that the strength goes up in this direction, right? And the weakness becomes, as we go from A, B, and C, C is the weakest of those three, okay? But there is actually a weaker force than any of those, and that's the induced dipole. And this one doesn't involve water because there's no dipole here. There's only induced dipoles. Okay, got that? So what the heck is this? Well, this is the force between two atoms or molecules, if they're nonpolar molecules, but two atoms that start out balanced. So let's consider a nonpolar argon, just a single atom of argon. Well, that nonpolar argon can become a dipole. It can essentially have more electrons on one side. They kind of all get pulled to one side, leaving a lacking of electrons on the other side, effectively making a positive end and a negative end. We've turned our argon into a dipole. But what would do that? Well, an external electric field created by an electronic device could do it, right? You could just, put it in a voltage. Or it naturally will happen when it experiences other atoms. How so? Well, consider. You have two argon. They come close to each other. The electrons in the two argons are going to, get repelled, right? So these electrons here push these other electrons away, and they're attracted to the positive nucleus. So they get pulled in the first place. See how that process works? Okay? And when that happens, well, now there's missing electrons over here, which means the attraction holds. That's how an induced dipole force gets created. But if this sounds like kind of a stretch, like everything has to go just right, you're correct in thinking that. This is a very weak type of force. It's the weakest interatomic or intraatomic or intramolecular force there is. It's a very, very weak force holding these atoms or molecules together. This idea of nonpolar atoms attracted to other nonpolar atoms with a momentary dipole, okay? So it's a force that isn't going to last, because what's going to happen is these charges are going to redistribute themselves, which is quite why we call it momentary. Because the charges, these electrons don't want to stay packed together. They're repelled from each other. They should all redistribute themselves in time. But initially they won't because of the dynamics, because an initial force causes a disturbance, and that leads to that momentary attraction, okay? Now, the bigger the atom, the more electrons, the stronger this momentary force. So big atoms like argon, there's lots of electrons, or iodine can have these fairly effective induced dipole attractions, okay? On the other hand, small atoms like hydrogen, it would be almost like unmeasurable small induced dipole. Another example, fluorine, right? Fluorine, not that many electrons, very, very weak, negligible induced dipole attraction. Almost there, but such a tiny force. And actually that idea of fluorine not inducing another dipole is how you make Teflon. You mix Teflon with carbon, and that creates a very smooth non-stick surface. And you know what's really cool? On the other side of this, these animals, geckos, searching for the name there, excuse me, but geckos actually use this incredibly weak force, the induced dipole force, to stick. That's how they do it. They don't use electrostatics. They're not using like a capillary force to stick. This amazing animal actually uses an induced dipole force to stick, the weakest force out there. But you might think, but it holds up its whole body weight? Well, that's because there's so many tiny little hairs on its feet, each doing that force. Okay? So which type of molecular attraction takes the least amount of energy to break? You guessed it, induced dipole attraction, the weakest type. However, when you have lots of hooks, like on Velcro, each hook force may be tiny, but the sum of all of those working together is strong. So in the case of the gecko, it's got millions of little hairs. That was its evolutionary trick, is it has so many little hairs, each creating its own induced dipole force, which allows it to stick to just about anything. Right? And it's such an amazing ability that didn't evolve in many other animals, but just a wonderful example of how, if you understand physics, you can understand the natural world around you. All right, well, that's the conclusion of our lecture all about molecular bonds. I hope it's been kind of a fun journey. I really enjoyed talking about the story of how all these different molecular bonds help explain how things are held together. Because of course, if we understand how things are held together, we can understand all these materials that we take for granted around us every day. Well, thank you so much for watching. It's been fun.